ኦኬ ሶ ባለፈው ካቆምንበት እንቀጥላለን። ከዚህ በፊትም ዲስከስ ስናደርግ እንደነበረው እዚህ ጋር you have a tank ለምሳሌ ይሄ ታንክ ሊሆን ይችላል like something like a swimming pool ሊሆን ይችላል so you have a fluid እዚህ ጋር you have a fluid and you have the container surround አርጎት ታገኛላችሁ so as our previous discussion ከላይ ያለው atmospheric air ከሆነ then atmospheric air on the surface ይኖረናል then ወደ ታች በምንሄድበት ሰዓት ላይ pressure እየጨመረ ይመጣል and we have said ይሄ pressure የሚጨምርበት rate ኢኒሻሉ ፒ አትሞስፌር ይሆንና ፕላስ ሮ ጂ ኤች ይሆናል ሶ ኤች ኢንክሪዝ እያደረገ ሲሄድ ፕሬሸሩም ኢንክሪዝ እያደረገ ይሄዳል ሶ እዚህ ስላይድ ላይ አንድ እንድታዩት የፈለኩት ነገር ምንድነው አትሞስፌሪክ ፕሬሸር ኦን ቦዝ ሳይድስ አክት የሚያደርግ ከሆነ ካንስል አውት ያደርጋል ሶ እዚህ ጋር እንደምታዩት you have atmospheric air the atmospheric pressure acting on the inside wall and then it also acts on the outside wall so you have the two cancelling out መጨረሻ ላይ net pressure distribution አችሁ ይሄን ይሆናል ማለት ነው so you can see እዚህ ጋር linearly እየጨመረ እንደሚሄድ ታያላችሁ so ከዚህ ኢኩዌሽንም እንደምናየው say አሁን ይሄንን like let's see how linear ስለሆነ we have y is equal to mx plus b አይደለ the mathematics so you have m being the slope x being the independent variable and b being the intercept so in that case p atmosphere is the intercept and h is the independent variable and rho g will be the slope and g constant ስለሆነ density vary በሚያደርግበት ሰዓት ላይ density decides the slope so density ትልቅ ሲሆን ስሎፑ ሰፋ ይላል and density ትንሽ ሲሆን ስሎፑ እየጠበበ ይመጣል so more steep እየሆነ ይሄዳል ማለት ነው so you need to remember this and this is very important and from our previous discussion ይሄንን እንዴት ይመስላል pressure distribution እንዴት ይመስላል ብዬ ጠይቄ ነበር አንድ ተማሪ ብቻ ሪስፖንድ አድርጓል and በስኬች መልክ ቢሆን የተሻለ ነበረ anyways we can discuss ይሄንን ዲስከስ ማድረግ እንችላለን so ቀደም እንዳነሳ ነው we have said pressure distribution will be p atmosphere plus rho gh and በዚህ መሰረት we have ለምሳሌ we have the first fluid so sorry for this poor sketch anyways the pressure distribution is expected to be something like this so on both sides atmospheric pressure act እያደረገ ከሆነ ለምሳሌ ለፍሉድ 1 እንደዚህ አይነት pressure distribution ይኖረናል so the only thing that changed ወደ fluid 2 ስንሄድ ምንድነው atmospheric pressure ብሎ ነው መጀመሪያ የተነሳው ሁለተኛው ላይ የፍሉድ 1 final pressure it's called that p1 በp1 ይነሳል so you will have p1 plus rho 2 g ብሎ h የራሱን h ከዛ ሪድ ማድረግ ይቻላል let's just call this h2 so ያ ይሆናል so something we expect ለምሳሌ density እየጨመረ የሚሄድ ቢሆን የፍሉድ 1 let's say density of 1 is less than density of 2 which is less than density of 3 then distribution ሊሆን የሚችለው ምንድነው let's say we have this sorry ይሄኛው አንደኛው slope ከሆነ then the slope is expected to increase so የሶስቱ pressure distribution ይሄንን ልዩነት ማየት እንችላለን ማለት ነው so this is have another sketch so if if we have this to be the wall ለምሳሌ and say ይሄ ፒ-አትሞስፌር ቢሆን and ይሄ በመጀመሪያ ፍሉድ ያለን ስሎፕ ቢሆን the next ላይ እየሰፋ ይሄዳል and the next እየሰፋ ይሄዳል ማለት ነው። so you can see እነዚህ ፍሉዶቹን ዲማርኬት የሚያደርግልን ላይን ይሄ ይሆናል ማለት ነው። so what you need to know the density decides the slope density slope-ን ዲሳይድ ያደርጋል። so ሶስቱ ፍሉድ የተለያየ ዴንሲቲ እስካላቸው ድረስ ስኬቹ የተለያየ ይሆናል ማለት ነው። okay, and we've also seen this. I've asked you to put down your thoughts, and so here we have a flow section, and in this flow section we have a manometer, and usually you use this manometer to measure the pressure drop along the flow. So we use this analysis. So from previous discussion and examples you will have this equation. So you have point 1. At point 1 you have pressure P1, and as you go down to point A you have density of the first fluid, that is rho 1, and times G times A plus H, and that A is as you can see in this that is as you can see here. So you have A plus H for the first one, and for the second one, that is from point B to point to the end of the second fluid, you have H, so that will be minus rho 2 GH. So if you remember, the reason we have minus rho 2 GH is because we are going up, and the next move to point 2 would be minus rho 1 GA, which will be equal to P2. So rearranging this and solving for P1 minus P2, you will have this equation. So this drop in pressure is the pressure loss in the duct, and you can measure it using just by measuring H and knowing the density of the fluid. Okay, so our next discussion is going to be on fluid statics, and this is about hydrostatic forces. So we're going to talk about hydrostatic forces acting on different planes. So here let's have an arbitrary object. So we have a plate here, and it has an arbitrary shape, so that is not important to our discussion. We're going to derive a relation for the general case. So if you have this plate, so the area of the plate is like this. So you have the fluid. This is the fluid, the one shown in light pink, and we're looking at the plate from the side. So you have this section, and you can see over here you can see small area dA, where we will analyze the differential pressure acting on it. So you have the surface at O, and as you go down, as we already know, pressure increases, and the rate pressure increases will be P naught. That is, if the pressure out here is P naught plus rho GH. And now H, since we are analyzing in the direction of Y, we have H being equal to Y sine theta. So as you can see, H is equal to Y sine theta, and we're gonna look for the resultant force, and we're going to look for the center of pressure to know where that force is acting, and this is a very important concept in our study. So This is what we have the resultant force, and the resultant force is going to be the integration of the pressure over the whole area. So we have said we have a differential area dA, and there is a pressure P acting at that point, and if we integrate that pressure equation all over, then we can have the resultant force. And we've also said that pressure will be equal to P naught plus rho g h, and h in this case is y sine theta. So as we continue, we have the resultant force being equal to integration over the whole area of P naught plus rho g y sine theta multiplied by dA. So just distributing this integration for the two terms, we have P naught, which is constant. So you have P naught, you have P naught, sorry, you have P naught being constant, so P naught integration of dA would be P naught A, and you have rho g constant, and also sine theta constant because the angle theta is constant, and integration of y dA over the whole area. So when we try to simplify this, we know that centroid, this is the equation, this is the formula for finding the centroid of an area, that is the first momentum of inertia. So that is yc is equal to 1 over area integration of y dA over the whole area. So rearranging, you can have yc a is equal to integration of y dA over the whole area. So we can substitute for integration of y dA. So as we substitute, we have the resultant force Fr being equal to P naught A plus rho g sine theta yCA. And let's continue further. Let's take area common for both terms. So we'll have P naught plus rho g sine theta yc the whole multiplied by A. Now this P naught plus rho g sine theta yc is the pressure at the centroid. So we can substitute pressure at the centroid instead of that term, and that represents the average pressure we have over the area. So your resultant force will be as simple as the average pressure times area. So you can calculate that average area using this. Now let's continue. Now we're not only interested in the resultant force, we're also interested at which point it acts. This is because, as you can see here, the pressure increases as we go lower, or as we go away from our axis. So we don't expect the resultant force to be at the center or somewhere above the centroid. So it's gonna be lower than the centroid. So you can see here you have P, that is the center of pressure, and you have YP over there also, and you can see that it's lower than YC. In any case, the main point here is that we'll have larger pressures to the left of the sketch, so you have the resultant force shifting to the left. So let's just have a moment balance at point O, as shown sorry, as shown here. So you can see point O right at the top somewhere here. So as we do the moment balance, this is what we're gonna have. We have YPFR, so we have YP over here, we have YP, YPFR is the moment by the resultant force at the center of pressure, and the integration of Y times PdA gives me the moment on every differential area. So we just calculate the moment on each differential area and add them up, so those two have to be equal. So substituting for P, because P is P naught plus rho gy sine theta, you will have integration of Y P naught plus rho gy sine theta times dA. So distributing the integration for the two terms, you will have this equation, and we know that P naught is constant, so P naught times integration of y dA over the whole area, plus we also know that rho g and sine theta are constant, so we'll have rho g sine theta integration of y squared dA over the whole area. And again, from our previous discussion, we have said that this integration of y dA relates with the centroid, and the integration of y squared dA relates with the second moment of inertia for an area. So from the definition of second moment of inertia, integration of y squared dA over the whole area would be the second moment of inertia of that area along the axis xx, and also that is it is about y, so the axis is xx and you have the point to be O. So substituting these values, you will have yp, you have ypfr is equal to p naught yca plus rho g sine theta ixxo. And this point, if this point O is different from the centroid, if it shifts from the centroid, you have this relationship where you can relate it with the second moment of inertia at the centroid. So adding this term to the previous equation, you will have ypfr equal to p naught yca plus rho g sine theta times I xx c plus yc squared a. So just doing just distributing this term and doing some manipulation, you can see that ypfr would be p naught, as you can see here, p naught yca rho g sine theta yc squared a plus rho g sine theta ixxc. And so as we continue, we can substitute for fr, because we already know that fr is p naught plus rho g sine theta yc, and if we divide all terms by p naught plus rho g sine theta yc times area, we can have the value for yp. So just doing mathematical manipulation, you can see that yp is equal to yc plus rho g sine theta ixx c at the centroid, that is the second moment of inertia about the centroid, divided by p naught plus rho g sine theta yc times a. And we can go further to simplify this and to put it for our purpose, and you will have if you divide this the numerator and the denominator, so if you divide the numerator and the denominator by rho g sine theta, then you will have this this final term. So yp is equal to yc plus Ixx about the centroid. So this is for a general surface. So whatever plate you have, this analysis can help you to find the resultant force and also the center of pressure. Okay, so here we have a special case of a rectangular plate. I'm not gonna go through this in details, but I want you to look at the arrangements here, and I want you to relate it with what you already know. So you have a plate here which is inclined, and you can see the pressure distribution. It increases as you go down, and you have theta, you have the S, which is the level at which the plate starts from the surface, and you have B and A being the dimensions of the rectangular plate. So the second case that it's showing is if the plate is vertical. So if the plate is vertical, it will be the analysis will be simpler, and you'll have theta being equal to 90 degrees, so the sine theta term will be equal to 1. And another case is where you have a horizontal plate, and if you have a horizontal plate, we know that pressure does not vary horizontally, so we expect the resultant force to be at the center. So that is what you see here, and you can go to the reference text, and you can see how this is derived. So it is very simple. You just need to substitute the area terms with the area of a rectangle. You just need to substitute the second moment of inertia for the second moment of inertia of a rectangular plate.